Hi, my name is Pascal Poupart. In this module, I will introduce inverse reinforcement learning. Let's quickly recap what is reinforcement learning. So in reinforcement learning, we have an agent who chooses some actions, they influence the environment, and then in return, the environment will produce some state and some reward that the agent can take into account in order to choose the next action, and so on. As a result, the agent has access to a sequence of state, action, reward triples, and then based on this, it will learn a policy that maximizes rewards. So the goal here really in reinforcement learning is to learn a policy. In Module 3, we covered the problem of imitation learning, which is closely related to reinforcement learning. So if you recall, in imitation learning, what is special is that we have an expert, and then we get to observe what are the optimal actions that this expert executes. So as a result, the data that we have really consists of state-action pairs, where the actions here, I denote them with a star to indicate that they are optimal actions. So then the goal is to choose actions that imitate the expert actions, and then we do this really by looking at what are those optimal actions as opposed to considering the rewards. In fact, in imitation learning, we observe the expert actions, but we don't observe necessarily the rewards that the expert receives. So the problem is different in that sense. So it's really a problem of imitation, trying to select the same actions as the expert. We can formulate the problem of imitation learning as a supervised learning task. And here we can see that whenever we have a state-action pair where the action is optimal and known, then we can treat it as a target and essentially do supervised learning. Now there are two issues with this. The first one is that when we treat this as a supervised learning problem, we are making the implicit assumption that the state-action pairs are identically and independently distributed. And unfortunately, that's not the case. So to understand this, let's have a look at a trajectory. So if we are in state S0 and then execute action A0, then this will lead to a transition to the next state S1. And this next state is obviously dependent on what was the previous action executed in the previous state. So it is in some sense correlated with the previous state action pair. So we can see here that all those state action pairs are correlated. And then the issue with this is that if we are learning by assuming a certain distribution of state action pairs, but now when we execute some actions that leads to a new distribution, then the principle of machine learning that we train on one distribution and assume that we're going to be testing on the same distribution doesn't hold anymore. So this can lead to some problems where the choice of actions like this will lead to perhaps new states with different distributions that will lead to more errors than otherwise. The second problem is that we cannot easily transfer a policy that was learned by imitation learning because it is tailored to a specific environment. So one easy example to understand that is in the case of autonomous driving. So let's say that you are familiar with the car that you own. So over the years, you've developed good skills and you know how your car will react in terms of, you see the sensitivity of the gas and the brake pedals. But now let's say that you go rent another car, and then this car has a different level of sensitivity. So what's natural is that you'll adapt your driving skills with respect to that level of sensitivity. But you see, if on the other hand you were driving exactly as if it was your own car as before, right, then you would not drive as well, and this could be dangerous. So imitation learning in that sense can be dangerous because a policy that is optimal in one environment may not be optimal when the dynamics change, even if it's just slightly. Whereas if we could somehow adapt this policy, then it would be much better. A solution to those two issues consists of inverse reinforcement learning. To understand what is inverse reinforcement learning, let's just quickly recap what is forward reinforcement learning. And in that case, we would take as input the rewards, so we observe them from the environment, and then we select actions that maximize those rewards. In other words, we try to find an optimal policy. In inverse reinforcement learning, we're going to do the reverse. So we're going to start with some knowledge of what is the optimal policy. And that could be in the form of a demonstration by an expert. And then based on this, we're going to try to infer what are the rewards that we're not able to observe. The idea here is that we're trying to find rewards for which the policy that we observe happens to be optimal. So the benefit of doing this is that now we can transfer the reward function to new environments. And in this way, you see if the environment changes, then a policy that was optimal before may not be optimal afterwards. But if the rewards stay the same, so if the goal stays the same, despite the fact that the dynamics have changed, then we can re-optimize the policy with this reward function in the new environment, and as a result obtain a better policy for that new environment. Let's formally define what is inverse reinforcement learning. So on the left side here, we've got our formal definition of regular forward reinforcement learning. And then we can see in red on the right hand side what are the differences when we consider inverse reinforcement learning. So for forward reinforcement learning, we observe the states and the actions as well as the rewards. And then our goal is going to be to find an optimal policy pi star when we have data that consists of triples, so S, A, and R at every time step. In contrast, in inverse reinforcement learning, what we observe are states with actions that are optimal, so that's why here we've got A star. But on the other hand, we don't observe the reward. So you see these are grayed out, indicating that this is not observable. And then the data consists of state action pairs, where again the actions are optimal. And finally, the goal is to find what is the reward function, or otherwise the reward distribution, for which the expert actions are optimal. So common applications of inverse reinforcement learning includes autonomous driving as well as robotics. And generally speaking, it's whenever we get to observe some expert demonstrate an optimal policy, and then we would like to use that in order to train an autonomous agent to mimic this policy. But we don't want to do this directly. We want to do this by understanding perhaps what are the goals or what are the rewards that the expert is implicitly optimizing. So this is very useful in autonomous driving because we can observe human drivers. These are expert, and then we can infer from that what are the social norms or what are some of the habits that humans follow when they're driving beyond just the rules of the road. In the same way, for robotics, there are certain types of robots, especially humanoid robots, where we can demonstrate what is a good solution to a task, and then we can get the robot to optimize that via inverse reinforcement learning. So the advantages, again, is that with inverse reinforcement learning, we're not going to make any assumption that the state action pairs are IID, and then we're going to be able to transfer the reward function to new environments and tasks. A general approach for inverse reinforcement learning consists of the following two steps. So first, we're going to find a reward function based on the expert actions that are known to be optimal. So schematically, you see we've got trajectory data. These are state action pairs where the actions are optimal. And then from this, we recover what is the reward function, otherwise the distribution over rewards. So that's our first step. Once we have that, then we have a second step where we're simply going to optimize a policy, and we're going to do that either in the same or very often in new environments. So in other words, you see we're going to take this reward function or distribution and feed that to a reinforcement learning technique that will then optimize for an optimal policy. Now there's several categories of inverse reinforcement learning techniques, and broadly speaking, we can divide these techniques into either techniques that do feature matching, maximum margin inverse reinforcement learning, maximum entropy inverse reinforcement learning, and also Bayesian inverse reinforcement learning. Now in this module, I'm going to talk about the first three. The fourth one is also important, but just to keep things relatively concise, I will stick to the first three techniques. An earlier approach to inverse reinforcement learning consists of feature expectation matching. Here the idea is that normally we would find a reward function R such that the optimal policy pi star chooses the same actions A star as the expert. Now the problem with this is that we may not have enough data for some states, and this is especially critical whenever we've got continuous states, because then obviously some states are never going to be visited. The probability of visiting a state is actually going to be close to 0. And then in that case, you see we may not have enough data to properly estimate the transitions and the rewards from those states. So one solution to deal with this is to say that we're going to extract features from the state action pairs. And the idea is that even if some states are not visited very frequently, if the features that we extract from them are similar to the features of other states, then we're going to be able to generalize better. So let's go ahead with this notion of feature. And here I'm going to denote by phi I the ith feature of the state action pair SA. Now, it'll be convenient to in fact consider a vector of features. So bolded phi is going to be this vector, and then based on that we'll also assume that the reward function is a linear combination of the features. So in other words, it's going to be a weighted combination of the features, and generally speaking it'll be convenient to write this as W transpose phi of SA. Now, based on this, the idea will be that we'll try to compute some feature expectations between the expert and our model, and then match them. If we have the same feature expectations, then the idea is that with the same features, now the reward function just being a linear combination of those features, we're going to implicitly recover what is the underlying reward function. Let's define mu E as a feature expectation of the expert E. And here by feature expectation, what I mean is that we're going to take a sum of discounted feature vectors for all the state action pairs that are visited by the expert in the trajectories that we observe. So you see this is a discounted sum similar to the discounted sum of rewards, but in this case it's a discounted sum of feature vectors. Now with this feature expectation vector mu for the expert, we'll want to come up with a similar feature expectation vector for the policy that we're going to learn. So let's call that mu pi, and the idea is that if we match the feature expectation vectors for policy pi and the expert E, then I'm going to claim that the value function of our policy pi will be the same as the value function for the expert based on the trajectories that are observed. Let's derive a simple proof for this claim. So to get started, just to review the notation, so phi is going to be our vector of features. Then we'll also assume that the reward function is linear in those features. So in other words, it can be written as W transpose phi. We also need the notion of discounted state visitation frequency. So phi here is going to be a count of how many times I end up in S prime when I start in S naught and I execute the policy pi. So this can be defined recursively, where first I count as 1 if S prime is the same as S naught. So here delta is a function that returns 1 when the two arguments are the same and 0 otherwise. So we add this to the discount factor times essentially how many times I'm going to end up in state S, and then from S after that end up in state S prime. Based on this notion of discounted state visitation frequency, we can now define the value function as just being how many times I end up in each state times the reward in that state. We can also rewrite the reward function based on the fact that it's a linear combination of the feature vectors. Then I can move the weight vector at the beginning of the expression. And then finally, I can rewrite the last part here as just my feature expectation vector mu. So based on this derivation, now we can see that when we match the feature expectations, then we can multiply them by W transpose in front. So just take a linear combination of those feature expectation, and then that corresponds to the value function, right? So this is what we derived right here. So that implies essentially that the value function will be the same. So you see now it should be clear that as long as I match my feature expectation vectors, then I will have the same value function, and that's essentially what I'm looking for. So matching the feature expectations is great in the sense that it ensures that I'm going to have a policy that has the same value function as what the expert executed, but the problem is that I'm doing this directly without necessarily retrieving a reward function. So again, here our goal is really to learn a reward function, and more precisely, because a reward function is parameterized by some weights W, what we're really after is to find this vector W. So if I match the feature expectation vectors, we just saw that the value functions are the same, but then this will work for any W, right? So I can pre-multiply both sides of the equality by W transpose, and then the equality still holds. And that corresponds again to the fact that the value function is going to be the same, but the problem is that this works for any W, right? So here we've got some indeterminacy with respect to the rewards, because if I match the feature vectors, then at some level it means that it doesn't matter what our reward function is, we will have the same value function regardless. So in order to determine a specific vector W, then we need some kind of bias that will help us identify one vector W over the others. And two common ideas in the literature consist of maximizing the margin and also maximizing entropy. So I'm not going to explain those two ideas in more detail. The idea behind maximizing the margin is to select the reward function that yields the greatest minimum difference, in other words the margin, between the Q values of the expert actions and other actions. So mathematically this corresponds to this equation here. So the margin is really this difference between the optimal action Q value and then the second best Q value, where here we're going to take the minimum with respect to all states. Maximizing the margin corresponds to solving the following optimization problem. So here we can see that we're maximizing the margin subject to some constraint, and the idea is that I've written this objective and those constraints in terms of the weights W that we're really trying to find, as well as the feature expectation vectors. So if you recall, mu here is a feature expectation vector. Now I'm going to use a bit of notation and define it with respect to a state action pair, and this will correspond to the feature for that state action pair plus an expectation of the feature vectors for the following states. Once we have this feature expectation vector for state S and action A, then we can rewrite the Q value as just W transpose times that feature expectation vector. So now we can replace the Q values that we had in the definition of our margin by this W transpose mu. So it gives us this expression. And then here you see we're optimizing what are the weights, but we also want to make sure that we're going to match the feature expectation vectors. So the idea is that we've already discussed before that it's a good thing to match the feature expectation vector, because that ensures we're going to have the same policy as the expert. But that in order to get a bias for the weights, then you see we have this objective here that will simply select the weights that will maximize the margin. So in other words, maximize the gap between the optimal action in each state and the second best action in that same state. This idea is good, but there is a problem. So maximizing the margin is somewhat arbitrary. Here the problem is that we might have some suboptimal actions that could be very close to the optimal actions. So here there's no reason why we would necessarily want to maximize the gap between the best and second best action. So what if we have a problem where it turns out that there are multiple actions that are optimal, or otherwise you see the second best action could be still very close to the optimal action. So when that's the case, then this idea will have essentially the wrong bias. A better bias consists of maximizing the entropy, and here more concretely this means that we're going to optimize this optimization problem. So the objective is the entropy of the distribution with respect to the trajectories tau, and this will be subject to a constraint where we're matching the feature expectation. So on the left hand side we've got the feature expectation of the expert, and on the right hand side is the feature expectation of the model that we're learning with respect to this distribution P of tau. Now, to understand in detail this optimization problem, we need some notation. So again, I'm going to denote by tau the trajectory that consists of a sequence of state action pairs. The feature vector of a trajectory tau is going to be denoted by phi, and that's again just a discounted sum of the feature vectors for the state action pairs in that trajectory. Then similarly we can denote by r of tau the cumulative reward of the trajectory tau, and that's going to be again just a discounted sum of the rewards in that trajectory. And then with that notion of rewards, then we can define what is the probability of a trajectory. And here we're going to appeal to the intuition that if a trajectory is more rewarding, so the higher is the amount of reward, right, then the more likely the expert is going to execute that trajectory. So here we can use the exponential of the amount of rewards as essentially the probability. So this will be the unnormalized probability. So to normalize it, you see we have this denominator here, but the idea is that the probability is going to be proportional to this exponential of the rewards. Now we'll see in a moment how this arises, but then the idea is that in maximum entropy learning, you see we make the probability of the trajectory proportional to this exponential of the reward, and what this means is that we don't assume that the expert is necessarily perfectly optimal, so it can execute actions that lead to pretty much any trajectory, but it's more likely to execute actions that will lead to trajectories with high rewards. That's the idea. And finally, the entropy, just as a quick recap, can be defined here as the negative of the probability times the log of the probability. It turns out that maximizing the entropy is mathematically equivalent to maximizing the likelihood of the trajectories. So to see this, I've written again our optimization problem for the entropy. So maximizing the entropy subject to matching the feature expectations. And if we take the dual of this optimization problem, so in other words the Lagrangian dual, then we will obtain this other optimization problem where instead we're maximizing the log of the probability of the trajectories subject to the probability of each trajectory being exponential in W transpose phi. So this is something that arises from taking the Lagrangian dual and rewriting the objective. And since you see our original objective happens to be convex, then the Lagrangian dual is in fact mathematically equivalent. So there's no duality gap, and it is mathematically equivalent, and then we can work with this one instead. And in practice, that's the one that's going to be easiest to work with. So in other words, maximum entropy is equivalent here to maximizing the likelihood of the trajectories that are observed from the expert. Let's expand our maximum likelihood objective. So we saw on the previous slide that this was our objective. Now let's expand that so that we can clearly see where is the W, which is the variable that we're trying to optimize. So if we just replace PW by its definition and then apply the log, we arrive at this expression. So that's the objective. So that's what we're going to try to optimize in order to find W. And one approach for doing this is that if we use a package like PyTorch or TensorFlow, then we can do automated differentiation, and then we can take steps in the direction of a gradient directly based on that. Now it's actually interesting to see what the gradient looks like, and I've included as well a small derivation here for the gradient. The idea is that if you simply take the derivative of this, you get this line, and then if you do some rewriting to reorganize the term, we see that the gradient at the end corresponds to the difference in the feature expectation vectors. So here this is the feature expectation vector of the expert, this is the one of the model, and you see the gradient is just the difference between those two. And what's kind of neat is that at an optimum, when the gradient becomes 0, right, then it would mean that you see the feature expectation vectors match. So this is consistent with you see our original goal where we wanted to match feature expectation vectors. So this happens as well when we maximize likelihood. So at convergence, once we reach an optimum, then we would be matching the feature expectation vectors. To do the computation of the gradient, there is one term where we need to compute the feature expectation with respect to our model. And here this is a feature expectation with respect to all the possible trajectories, and the problem is that this expectation will become exponentially large because there's exponentially many trajectories. So since this is intractable, we're going to have to approximate, and one simple way of approximating is just to change this expectation into an average over some samples. So here what we could do is just sample some trajectories from our distribution P of tau and then take the average of the resulting feature vectors. The problem with doing this is that we may not have a simple way of sampling from the distribution P of tau. So in most cases, in fact, this will not be possible. And instead what we could do is just sample from some base distribution. We're going to denote it by Q. So Q tau is this base distribution. And then we're going to reweight those samples by the ratio of P of tau divided by Q of tau. So this really corresponds to importance sampling. So in other words, you see we have our sample average, but because we sample from the base distribution Q, then we reweight those samples by taking the ratio of P of tau divided by Q of tau. Now you might ask, well, how do we choose Q? There are many ways in which we could choose Q. The simplest way would just be to consider a uniform distribution, but what's better is to choose Q to be close to some of the demonstration distribution of the expert, or ideally to be close to P of W of tau. So in other words, you see that's the distribution ideally we'd like to sample from, so we can make Q as close as possible to that would be great. We now have all the ingredients to define an algorithm for inverse reinforcement learning. So in fact, on this slide, I'm showing the pseudocode for a specific implementation of maximum entropy inverse reinforcement learning. In this implementation, we're going to assume that the rewards are linear with respect to the weights as well as the features. In this implementation, then the main computation will really just correspond to a loop in which we're going to update our models. In other words, update the weights simply by taking steps in the direction of the gradient. And this will be the gradient of our log likelihood objective that we saw before. So if you recall, the gradient again is just this difference between the feature expectation of the expert and the feature expectation of our model. But then there's some difficulty in computing this feature expectation because the number of trajectories tau can be exponential. So then we do an estimate, an approximation by sampling. So we sample some trajectories tau from our base distribution Q. Let's say we get n of those trajectories. Then we take the average of those n trajectories weighted by the importance, so that's essentially the ratio of P of tau by Q of tau. So that's the algorithm, very simple, right? Just take steps in the direction of gradient, update the vector W, and then you stop when you converge, and that's what you return, because W defines what is the reward function, right? So and if you recall, the goal of inverse reinforcement learning is to find the reward function. Generally speaking, it would be better if we didn't have to assume that the reward function is linear in terms of the weights and the feature vectors. So if we go with nonlinear reward, perhaps we can set the reward function to be a neural network where W denotes the weights of that neural network. When we define the reward function in this fashion, then we can also have a cumulative reward for a trajectory tau as just being the discounted sum of the rewards for every state action pair. So this is the same as before, but then we can use that to rewrite our likelihood objective as well as its gradient. So the likelihood objective used to have some terms here that were essentially W transpose times phi, but that really corresponds to the reward function, so we can just plug in the reward function here, and then same thing at this location. Then when we take the gradient with respect to W, we'll have to take the gradient with respect to the rewards as well, and that's what occurs here. So in other words, our gradient now is going to be the difference of the expectation of the gradient of the reward with respect to the expert trajectories, minus, you see here, the again expectation of the gradient of the rewards, but with respect to our model. We can adapt the pseudocode that we saw earlier for maximum entropy inverse reinforcement learning to use a neural network for the reward function. So this is the general case where the rewards are nonlinear, and here we'll just have R of W to indicate that it's some function, could be a neural net, any function, in terms of the weights W. What changes is essentially what is highlighted in red here. So first, you see for the expert feature expectation, then we simply replace the feature vector by the gradient of the rewards. And then same thing for the model feature expectation. So the feature vector is replaced again by the gradient of the rewards, and then that leads to a gradient that's just the difference of those gradient expectation, and then we'll take a step in the direction of the gradient as usual to update the weights. As we discussed before, inverse reinforcement learning allows us to recover a reward function, but ultimately, you see, we want to use that reward function to obtain a policy. So how do we do this? Well, here there are two choices. The first one is that we could just optimize a policy based on this reward function that we obtained by using our favorite reinforcement learning algorithm. Another possibility is in fact to obtain a policy directly based on the distribution of the trajectories that we have. So here the idea is that we can induce a policy simply by looking at what is the probability of choosing an action A after arriving in state S and the trajectories that we already have. So to understand that, let's say that we have a trajectory that corresponds to a state S, action A, and then more state action pairs that are captured by tau. So tau is normally a trajectory, but now I'm going to use S8 tau as being, I guess, a longer trajectory that starts with S and A, continues with tau. And the idea is that now if I want to know with what probability, according to my trajectories, I would select action A given that I'm in state S, then I could simply compute what is the probability of A given S according to my model, right? So normally you see this probability is for a trajectory. So now instead what I'm going to do is look at the trajectories that start with state S and action A, and then continue with more state action pairs that I'm just denoting by tau. So I'm going to take a sum of the probabilities of those trajectories, and I'm going to divide that by a normalization constant that is essentially the same. So again, the probability of state S, action A prime, and trajectory tau prime. So that's essentially all the trajectories that start in state S, but now I don't care about what follows. So it could be any action A prime and any trajectory tau prime. So this will give me, you see, an estimate of the probability of a given S according to the trajectories that I have and the probabilities that come from my model. So if I expand this, right, the probability of a trajectory is just the exponential of the rewards earned in that trajectory, and so it gives this expression. So this would be another way of obtaining a policy that matches, you see, the probability of choosing a certain action A following a state S. To conclude this module, let's have a look at a demo that illustrates this maximum entropy inverse reinforcement learning technique. So the particular technique here that we're going to look at is the one that was proposed in guided cost learning, deep inverse optimal control via policy optimization, and it corresponds more or less to the pseudocode that I explained earlier. So it has some additional bells and whistles, but otherwise it is the same idea in spirit. So in this work, what the authors have done is essentially train a robot by essentially learning from demonstrations by a human expert. So you see the human shows the type of motion or gestures that the robot should perform in order to accomplish a task. They compare this to some other techniques that are not so good, and then finally when it's their technique, you can see that it works quite well. So this is one task here, so putting dishes, but then they have some other tasks. So another one here is to pour a cup. So same idea, so they demonstrate what the motion should be by using a human who just operates the robot. And then after some of those demonstrations, then they will try it. So some other algorithms are not so good, and even if they're trying quite a bit, it's still not that good, but then with their technique it works well. Okay, so this is it for this module. So thank you for watching, and I hope that this was useful.